Let's continue our discussion of logical statements. Suppose you have a logical statement, call it P. It will either be true or false. Those are the only two possibilities. Now suppose I want to look at the statement not P, or the negation of P. If the original statement P is true, then the negation of P is going to be false. By the same token, if the original statement P is false, then the negation of P will be true. And we can organize those values, and those are the only two possible values. We can organize them in something called a truth table. Now, a truth table simply takes the statement or statements and gives them a column and organize it in a tabular fashion. So if the original statement is true, the negation is going to be false. And if the original statement is false, the negation will be true. And if you just put that information in the table, when P is true, that's here, the negation of P is false, that's here. If P is false, that's here, then the negation of P is true, that's here. So all I'm doing is taking those values and organizing them in a table. That table is called a truth table. So this is the truth table for the negation of P, and it is the first and simplest truth table we'll be working with. I hate to say that you have to memorize this, but you have to know this, that when P is true, not P is false. When P is false, not P is true. So that's something that you will have to know and be able to use. So that's our first truth table. What we want to do now is build more truth tables. We want to build a truth table for each of the connectives that we've discussed. We've talked about and, or, the inclusive or actually, not, if then, and if and only if. So we build a truth table already for the negation, the not. We want to do it for the other four. So let's get right to that. I will say this, that the truth table for the negation of P is going to be the simplest of our truth tables because it only has one statement in it. It only has the P. The other four, and, or, if then, if and only if, have both P's and Q's. They have two statements. So obviously the truth table for the other four connectives will be somewhat more complicated. So keep that in mind as we move forward. I'd like to start off with the truth table for P and Q. Now obviously we will need a column for the statement P, we'll need a column for the statement Q, and the truth values will have to go in the third column, so we need a column for the logical expression that we're building the truth table for, which in this case is P and Q. So in the first case there was only a P, so I didn't need a column for Q because there was no Q. I was just negating P. But here I've got a P and a Q, so I have to have an extra column. Now also keep in mind that a truth table's got to list every possibility, everything that could possibly happen, every combination. When there's only a P, it can only be the true or false, but when you've got two statements, P and Q, you've got more possibilities. In fact, if you have a statement made up of n different simple statements, then it will have 2 to the power of n rows in it. Well, this time we have a P and a Q, so a truth table for a statement with two different simple statements will have 2 to the second, which is 4 rows. So I know already that my truth table will have 1, 2, 3, 4 rows. Okay. Now, what goes in those rows? Well, you want to take, I call it seeding. You want to seed that table with every possible combination of true and false. So if you start off, well, what could happen? Well, both statements could be true. P could be true, Q could be true. What else? Well, P could be true, but Q could be false. It's another variation. Or it could be reversed. P could be false, and Q could be true. And the last possibility is that they're both false. So if you think about it, those are the only possible combinations of T and F possible if you only have two simple statements. So I've seeded our truth table. So all that's left to do is complete the last column, which is the truth value of the connective that we're looking for, in this case the and. And what I would suggest is just a common sense approach. Just make up a simple sentence and think about the meaning of it. And I think you can decide what the truth values will be. And that's the approach I'm going to take. Let's just make up a simple sentence with an and in it. I'll choose something like this. Kids eat food and fish swim. That's a compound. It has the and in it. And I pick things that are obvious to see their truth value. Suppose I start off with both statements being true. Kids do eat food, fish do swim. So if I say kids eat food and fish swim, I think we would all agree that that compound sentence is in fact true, because kids eat food and fish swim. Move to the next line in the table and do the same thing. Go down and let P be true and Q be false. Make up a sentence like that. Well, how about staying with kids eat food as being true and something like rocks swim? Well, obviously rocks don't swim, so that's clearly a false statement. So I've made up a sentence that says kids eat food and rocks swim. Our use of and is pretty much the same as in English, and that is that both statements have to be, both simple statements that make up the compound statement have to be true in order for the and to be true. So although kids do eat food, rocks do not swim. So if I say kids eat food and rocks swim, that is a false statement. And if you think about it, if you go to the next line and reverse it, put a false statement and in with a true statement, it doesn't really change things. I'll move the rocks swim over to the left and the kids eat food over to the right. Rocks don't swim, so that's a false statement. Kids do eat food, that's true, so I've got a false and in with a true. And again, unless they're both true, an and is false. So that compound sentence is not true, so the resulting compound statement is false. The last possibility is for both P and Q to be false. If you make up a sentence like rocks swim and flies have 18 legs, and if I say rocks swim and flies have 18 legs, then I think we would all agree that that statement is not true, so the resulting connective is false. But after having gone through this, we now have our second truth table. This is the truth table for and. So we're building up our truth tables. We've got the negation truth table and we've got the and truth table. Let's keep going. What if I want to get the truth table for the connective or? That's what I've done here. The seeding stays the same. You still have those 4 rows with all combinations of trues and false. So that seeding doesn't change as long as you only have 2 simple statements. And the procedure is the same. I want to look at each row of those and decide what the resulting compound statement should be, true or false. And again, I would make up a sentence, just a simple sentence that helps you think this through. And I decided to use pretty much the same as I did before, except I'm changing and to or. So I'll choose kids eat food or fish swim. Kids do eat food, that's obviously true. Fish do swim, that's true. So if I say kids eat food or fish swim, I think most of us would say that is a true statement, so that the resulting logical statement is true. Now, I will say, going back to that one, this is the inclusive or. It allows both to be true. We're really not discussing the exclusive or at all, but if you have an exclusive or, it would say that if either P or Q is if they're both, I'll say, if they're both true, then the result would be false. But we're doing an inclusive or. So it allows the possibility of both pieces being true. Going to the next line. If I let P be true and Q be false, and again make up a sentence such as kids eat food or rocks swim. Kids eat food is true, rocks swim is false. If I say kids eat food or rocks swim, in the common sense English meaning of that compound sentence, that would be true. And so with an or, what you're basically saying is if either or both pieces that make up an or are true, then the result is true. So if I go to the third line, which I reverse it, I still have one false and one true, so I might say rocks swim or kids eat food, and that's again a false ored with a true. So if I say rocks swim or kids eat food, I think we would all agree that that is a true statement. And finally, the fourth row, make up a sentence with both pieces false. Rocks swim or flies have 18 legs, and I think we would all agree that that is a false statement. Having gone through that, we now have our third truth table. So we have our negation, our and the or, which is actually an inclusive or. And as I said, we don't really deal with the exclusive or. There's an easy way to remember these three truth tables, and if you just look at them, you can see how easy it really is. If you're trying to remember the negation, all you have to remember is that it changes the truth value to its opposite. So true becomes false, false becomes true. If you're looking at a way to remember the truth table for and, you can easily see there's only one case where the compound statement and comes out true, and that's if both P and Q are true. So I would say I would remember the and by saying it's only true if they're both true. Similarly for the or, there's only one place where the or is ever false, and that's only if they're both false. So my memory aid is to remember negation by remembering to change the truth value to its opposite, remembering and by remembering the one case when it's true, and that's when both P and Q are true. And for the or, remembering the one case when it's false, and that's when they're both false. Let's pause and take a look at an example where you might use some of these truth tables. We've done 3 of the 5 that we are going to eventually do, but let's stop with 3 and just find a problem where that would prove useful to know these truth tables. This particular example says construct a truth table for, and this logical expression is written out here. And to do this, you've got to realize that this logical expression has a negation in it, so you want the truth table for the negation. It also has an and in it, so you'll want the truth table for the and. We've done 3. The third one is or, but this one has no or in it, so that one doesn't apply for this particular problem. Once you do that, then you have to notice that there are actually 2 simple statements within this compound statement. There's a P and there's a Q. So you'll need a P column, you'll need a Q column, and then of course you'll need a column for the entire expression that you're attempting to find the truth value of. As we said before, if you've got 2 simple statements, then you'll have a truth table with 4 rows, and you want to seed it with every possible combination of true and false, and we've gone over that before, but you can have true, 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 false, false, true, or false, false. That's every possible combination. Once you get the truth table set up that way, then you just want to evaluate it line by line. So we'll start off with the first row, P being true, Q being true. And if you plug in a true for P and plug in a true for Q, you get that expression for the first line. And then if we go to the second line, if you plug a true in for P and a false in for Q, you'll get that expression. Then going to the third line, if you put a false in for P and a true in for Q, you'll get that. And finally, if you put a false in for P and a false in for Q, you'll get that. Notice we're just doing a direct substitution of either T or F for the appropriate statement P or Q. Once you get to this point, start looking for simplifications. For instance, I know immediately that the negation of a true statement is false, so I can replace all the not T's with F's. And I also know that the negation of a false is true, so I can replace all of the not F's with trues. And that takes me to this point. Now we want to work inside the parentheses, one row at a time, and simplify these ands. Now we have the truth table for and over here, so we know what to do. And remember, we also had a shortcut for remembering an and. The shortcut for remembering and is only true if they're both true. Now if you look through here, you can see there's only one case where they're both true, and we're looking in the middle part, but let's just take it one at a time, at least in the beginning, go slow. If I look at that first expression in the first row, false and false, looking over here, false and false is false. So you put false in. Moving down to the second row, you've got false and true. Well, false and true is false. So you put a false in. Moving down again, true and false. Looking at your truth table, that's false. You put that in. And finally, true and true. In fact, that's the only one that's true. So you put in a true. But you're not done, because you still have these negations out front. The negation of all the falses will be true, so you can put true in place of that, looking at your negation. And then lastly, the negation of a true is false, so you put that in. So when your last column has been completely simplified to trues and falses, you have constructed a truth table for that statement. So this truth table tells you for what values of P and Q that statement is either true or false. Just a simple example of what you can do with truth tables. There's also a concept called equivalence that's extremely important, and by definition, two logical statements are equivalent if they have the same variables with exactly the same truth values. Simple example. Are these two statements logically equivalent? The negation of P ANDed with Q and the negation of P ORed with the negation of Q. Well, what does it mean to be logically equivalent? They have to have the same variables with exactly the same truth values. Well, how do you document truth values possibilities? You do a truth table. So the trick with this is just to complete a truth table for each statement and see if they're identical. So you set up a structure. Both of those statements have a P and a Q, so you'll have 4 rows in both cases. And you put, for the third column, the first statement over here, and the second statement over here, and you're going to do each of these separately. So let's start with this one. Let's start with the one for the negation of P ANDed with Q. So we do just what we did in the previous example. You start off with the first row and you put in true for P and true for Q. And you keep moving down. In the second row you put in true for P and false for Q. Keep moving down. In the third row you put in false for P, true for Q. Then in the fourth row you put in false for P and false for Q. And then you start simplifying just as we did before. Remember, I'm going to sort of use my little shortcut memory technique now. I'm doing ands, and the way of remembering an and is that it's only true if they're both true. And if you look through the whole list of these, the only one where they're both true is the first one. So that means that the first one will be true and the rest of them will be false. But we're still not done, because we haven't dealt with the negation yet. So we still have to negate each of them, but that's easy enough. The negation of true is false, and the negation of false is true. And now we're done. Now we've done the truth table for the first statement. Now we're going to go over here and do the truth table for the second statement and look and see if they're identical or not. So forget the first one now and move over to the second one. Start off the same. True for P, true for Q. Moving down to the next row. True for P, false for Q. Moving to the next row. False for P, true for Q. And finally the fourth row, false for P, false for Q. And then you simplify. Notice in the first one over here, the P and Q was inside the parentheses, so you did that first and then you negated. Here, you're going to negate the P, then you're going to negate the Q, and then lastly you're going to OR them together. So the first thing we're going to do on this right hand table is to look through and notice that the negations are easy. If I want to negate all the trues, I make those into falses, and if I want to negate all the falses, I make those into trues. And now I go back and finish it off. Now I'm ORing. So in the first row, I'm ORing two F's. Now remember the rule for remembering ORs, and that is that it's only false if they're both false. So there's only one case where they're both false. The other cases, they aren't both false. So that will be false, and the rest will be true. And then you compare. Are they equivalent? Well, you got a false. True, true gives you false over here. True, true gives you false over here. True, false gives you true over here. True, false gives you true over here. False, true gives you true here. False, true gives you true here. False, false gives you true here, and false, false gives you true here. They are identical. So yes, those two statements are logically equivalent. It's a simple concept. Another important thing we want to talk about here are deMorgans laws. These are easily provable. In fact, we really just proved one of them in that last equivalence, but beyond that I won't go into a proof of these, but we will use them. The first of deMorgan laws tells you how to take the negation of an and. So if you have an and you want to negate it, deMorgan's law says that's equivalent to the and changes to an or, and the negation shows up in both places. It's almost like the negation is almost like a minus sign in this instance. The negation applies to each of the statements, and then the connective flips. So if it was an and, it flips to an or. So they're easy to remember. And the second deMorgan's law tells you how to take the negation of an or. And you can probably guess what it's going to be now. You distribute the negation, so you get a not P, you get a not Q, and you flip the connective, so the or becomes an and. So deMorgan's laws are really very easy to remember. To negate an and, you make it an or and put a negation on each statement, and to negate an or, you make it to an and put a negation on each of the statements. So those are really easy to remember. And like I said, we had just proven one of those, because that when we showed those two statements were equivalent just a minute ago, it was one of these two. I actually not sure which one it was without going back. It doesn't matter, but that's how you would prove the other one as well. Just prove that the two things were equivalent to each other. Now we will write, instead of writing the word equivalent, we will use this symbol with three horizontal lines. That's our symbol for equivalence. So you could write deMorgan's law a little more mathematically by replacing the word equivalent or logically equivalent with the symbol. It's just a little more compact way of writing it. You're using this symbol instead of the word equivalent. In any case, those are deMorgan's laws, and they're useful for finding the negation of an and or an or statement. Ah, there it is. We had proven this first one. The one we worked a minute ago was that one. We showed that we did the truth table for this one, and we did the truth table for this one, and we showed they were the same. And that's how you would do it. If you wanted to prove that these two were equivalent, you do the truth table for this one, the truth table for that one, and show that they come out exactly the same. So we had done the truth table proof of the first deMorgans law earlier. Okay, what will we do with deMorgans law? Here's an example. It says use deMorgans laws to write a statement logically equivalent to this statement. And the statement says it is not true that my paper was it was not true that, let's just think of that all as one thing. My paper was well written and my paper did not get an A. So sort of look at the sentence that way. First thing you need to do is convert that back into symbols. So you might want to let the phrase, it is not true that, be written as a negation. When you say something is not true, then you're negating. So that phrase, it is not true that, becomes a negation. And then you're negating everything after that, and since what you have after it has an and in it, you better use parentheses. My paper was well written. We'll call that statement P. And, the symbol for and. My paper did not get an A. We'll call that Q. So P goes here, Q goes here, and goes here, and the negation goes here. So you're translating that sentence back into symbols, into a logical statement written with symbols. And now, if you use the first law, this is the negation of an and. So you go back up here and see the negation of an and is the first one, the negation of an and. And so you can rewrite that as the negation of P, the and flips over and becomes an or, and then the negation of Q. And now that you've written it that way, if you take the right-hand side of that equivalence and write it back in words, what would you have? Well, you're trying to take this right-hand side and turn it back into words. So what does not P mean? And what does not Q mean? Well, P says that my paper was well written, so not P would be my paper is not well written, or was not well written. And Q is the statement my paper did not get an A, so the negation of that would be my paper did get an A. And notice I sort of skipped over it, but the first deMorgans law says the and becomes an or when you're negating, so that and in the original problem becomes an or as I'm translating. So the translation of this would be my paper was not well written, or my paper did not get an my paper did get an A. Let me say that again. My paper was not well written, or my paper did get an A. Just have to practice these. The ideas are fairly simple. You have to know your truth tables. You have to know deMorgans laws. But the ideas beyond that are fairly simple.